So whenever you have the case that you, yeah, it mentioned that you don't want to exceed 128 bytes. Typically, you will not exceed it unless you create too many global variables. What can you do, right? Well, what you can do is just like to exceed that limit is to create, for example, segregated list. So in segregated list, remember that we have a lot of entries. Let's say you have 64 entries, and each entry is 8 bytes. So that's going to be 512 bytes easily, right? So this is how you can easily exceed that limit. So if you just put that array as a global variable, right? But what can you do? How can you place that array without exceeding the limit? Well, recall that, one way to declare this array is, okay, right. One more time. So let's say this is your list, and this has struct node, maybe next, struct node previous. I'm just, doesn't matter what the structure is. Maybe your structure is entirely different. Doesn't matter, right? Like fundamentally, probably somewhere you're gonna have pointed to the first element in the list. Struct node array, maybe seg list 64, something like this, right? So this is where you will easily exceed the limit, because this is where it will create 512 bytes. Yes, so how do you prevent that? Well, the way that you prevent this is, remember that you can put also stuff on heap directly. So why wouldn't you allocate this 512 bytes in the beginning of the heap, right? So before you even put this prologue, whatever, epilogue, right? So whatever you put here, fake footer, prologue, and so on, right? Just put it in the very beginning of the heap. So this is double waterlined. This is still going to be double waterlined as long as the number is right. Right. So in this case, 512. But if you have 63, that's not going to be double waterlined. So be careful, right? Because 64 will be double waterlined, 63 will not be, because you only have one pointer in seg list. So make sure if you need to allocate a little more, right? So that it's still double waterlined. And then instead of this, you will create something different. You will create struct node double star seg list. So fundamentally, you can still access the seg list the same way, like as you do with this guy, right? But now this is going to point, so you're going to initialize that to the beginning of this, right? So and then seg list, you still have seg list 0 points to node star, right? Seg list 1 points to node star, and so on, right? Because the way that in C, pointers and array work, right? So you can you use the same notation for both arrays and pointers. So this is going to be a pointer to the beginning of this heap in this case, right? And that way 512 bytes is going to be allocated on the heap, not in the global area. So does it make sense? So again, be careful to not exceed that limit. Do not exceed 128 bytes. Just put it directly inside the heap. I guess maybe it's not, I mean, it's going to be probably more concern for after the checkpoint, right? So when you implement something more complicated, right? Than just an explicit list. Because for explicit list, it's still probably one pointer, like it's still probably going to be fine, right? But for seg list, it's going to be a problem. Also, if you implement something different, like something that requires a lot of global variables, please be sure that you don't exceed that limit, right? So just count how many variables, how many global variables you have, and multiply it by the size, and you will easily check that. Okay, go ahead.
So how many global variables do you think we would actually need?
Well, I mean, I would say 128 bytes is probably more than enough, right? Unless you want to start allocating arrays. So you will have like maybe a list of the first element of the free list if you use an explicit list. Maybe you're gonna have a pointer to the beginning and end of the heap, right? I don't know, right? So how you're gonna keep track of that, right? Depends on whether you have implicit or explicit allocator, right? But we are talking about some small number, something that still within like, not more than like maybe 3 or 4 variables, right? So you should still be fine within this 128 byte limit. But once you start in allocating arrays, this is where you're gonna have a problem, right? Or maybe some bad implementation of the memory. Sometimes I saw that people were able to exceed it even in in some trivial memory allocator, right? But also the other thing to mention, if you follow the textbook, don't just copy and paste the code, because in the textbook we had this so we had this macros defined, right? So again, it's one reason you don't want to copy and paste, right? Because you probably need to replace this macros with inline functions or constants, because we don't allow macros. I mean, and in general, you are not allowed to copy and paste, right? So I said you can get inspired with this code, but you will still have to change it heavily, right? But also in the textbook, they also do it for 32-bit. You're gonna have 64-bit. So a lot of changes will happen anyway, right? Okay. Any questions? So how many of you are already done with project one? Just curious. Checkpoint. Like no, like I mean, you want just checkpoint, not the final version, right? So of course, they're still working. Okay. Okay, today we're going to get started on a different topic. It's also a very important topic. It's going to take several lectures. I mean, I guess probably 3, but at least 2 lectures, right? 2 or 3 lectures. So this is virtual memory and how we support memory virtualization. So for that, there is also a textbook chapter, which I'm going to post the number after the lecture if you're curious. But I mean, the textbook is different. For memory allocated using CS app, textbook for this one is the OS free easy pieces, the main textbook. Yeah, I also wanted to make some additional announcements for project one. So for project one, make sure you understand why we have this double linked list versus single linked list. Remember, I said that once you implement explicit lists, you need a double linked list. So the reason is that when you do coalescing, you looking at your neighbor nodes. In your neighbor nodes, even though those are your neighbors in the terms of memory addresses, they can appear in any place in the free list if they are free, right? So let's assume some of this block is free and you want to coalesce with it. So you have to remove it from a free list, but it's completely unknown location where it is, right? So it may be in the beginning, maybe in the end, maybe in the middle. So you need to have a way to remove elements like from any place in constant time. So double linked list helps to do that. Because for double linked list, you can go to the previous node, you can go to the next node, you can update their pointers. You always have that information. So even the corner case, like first element in the list, you have that like probably null pointer, you know that you have to update the first pointer in the first element. That's the first element of the list. By the way, it's up to you whether you want to use cyclic lists or whether you want to use a regular double linked list which points to null or previous points to null for the first element, and next for the last elements also points to null. That's, I guess, probably more common way to implement double linked list. But just remember that you need to handle those corner cases for the first element and for the last element. So for the last element, next is null, right? So and therefore there is no element to update after that. So for the first element, there is no element in front, but more importantly, you have to update the pointer to the first element in the list. So that means don't forget to update that pointer. So if you're in the middle, then it's fine, right? So in the middle, it's going to be a straightforward procedure. So also, we use Slack for project discussions and for any questions. So I get quite a few questions by emails, and sometimes it's the same question over and over again. So this is why we have the Slack, right? So discussion, so that whenever you post a question, some other people can check that, and so hopefully they will find an answer, right? Also that allows to get a faster response, because it's possible that, let's say I'm busy, maybe TAs can answer, or maybe TAs are busy, I can answer, right? So it just allows any of people who are looking at these questions to answer. Maybe even some other students, right, can help with that questions. That's also fine, as long as you are not sharing any code or anything like this, right? So if it's just a conceptual question, which just requires understanding of the project, that's fine, right? It's totally fine, right, to discuss those, but don't post any code. If you need to discuss something like privately related, maybe not a technical question, but something privately related about the course, some question, then you can have a private message to T or to me, whatever you find more appropriate. Yeah, so also I've seen that quite a few groups were not created according to the convention, right, that I mentioned. So the convention was a small group and no space and number, right? I've seen that a lot of people created like capital group, like hyphen group, space group. That's probably fine for project one. Just in future, don't do that. Just follow the convention that I mentioned. But still, there were even worse cases when people created something like my group, whatever, right? So those groups which completely off, right? We don't follow the canvas allocation, right? So those are going to be deleted without any warning, right? This time I'm okay, right, to kind of allow this group, capital group or small group, or like group space, whatever, right? As long as it corresponds to the group that you are in Canvas, right? But if, let's say, you are joined some different group, then again you will be removed without any warning, right? So because you are blocking someone else from joining that group. So I've seen some cases when people erroneously join some different group. So again, in this case, I will delete you from that group. So your group allocation should be the same as in Canvas. So also, if you have any conflicts, I think we already had situation like not like I mean, I think 1 or 2 situations like this, when there was some conflicts, people are not responding or something like that. So in this case, we just split the group most of the time at this point, because this way it allows you to focus on the project. Because we cannot just, I mean, some people are already doing something else, unless you're both in this initial stage of the project. We will just split the group, and so there is no point to even combine with anyone else at this point. So the project is completely doable by one person, and a special checkpoint, right? So I think this is totally fine if you need to work alone. Just if your partner is not responding, let us know, and we will just split your group. So from my past experiences, the best way to deal with this issue, because if we give you another partner, the same issue may happen, right? So and you don't have time already to experiment with that, right? So it's better to split it so that you can work and focus on the project. So let's so as I said, today we're going to talk about new topic, virtual memory, and let's take a look at the system that is using virtual addressing. So by the way, before I completely switch topics, does anyone else have any other important questions about project 1 or something like this? Okay. So if you have any questions, post them on Slack, right? But I assume you are working towards the checkpoint deadline, right? There's still some time left, right? So please work on it. And I don't think that the checkpoint is hard. In fact, the checkpoint version, as I said, can be really simple. Just as long as even if you have troubles with Cal lesson, but still can pass the test, that's fine, right? But the point is that you still want to implement something, right? I've seen sometimes people would try to just call basically memsbrk from a malloc. That's not good, right? So because you definitely want to have some memory allocator, right? I I know the test, the checkpoint test will not test it rigorously, right? So sometimes it will give 50 points for that dummy version, so to say, right? But you don't want to implement this, because we're going to check that. Please implement some memory allocator, whether it's implicit list or explicit list, it's up to you. Even if it's not doing Cal lesson, at least it tries to recycle some blocks, right? Because that's the whole point of the memory allocator. Otherwise, if you just redirect to memsbrk, you're not implementing the memory allocator. You're just redirecting this to the OS, and you're not freeing any memory, right? Effectively, because you have to be able to scan the previously freed memory in malloc. So not just calling memsbrk all the time. So it may be really inefficient memory allocator. That's fine, but at least it makes some effort to recycle previous memory. For checkpoint, that's fine. For the final version, you want to implement something that will be good in both performance and memory utilization. Okay. So going back to the topic that we discussed today, right? So what is this? How the system that uses virtual addressing work? Well, if you don't have any virtual addressing and just have main memory and CPU, that's what you got, right? So whatever the address you have on CPU, that's the address you put on the address bus, and that's what you're going to retrieve from memory. So now if we deal with virtual addressing, the virtual address that CPU produces, or whatever it maybe from the instruction, it has to be translated through the memory management unit. So a memory management unit, also known as MMU, and that's what the block you see on this picture. Sometimes, I mean, nowadays it's typically part of the CPU chip, but fundamentally it's not. I mean, you can think of it as it's just different block, not necessarily directly related to CPU, but typically it's on the same chip as the CPU. The memory management unit is going to translate virtual address to a physical address. And the physical address, so the CPU itself deals with virtual addresses. So memory management unit will do the translation, and then the physical address is something that you put on the memory bus as an address bus, and this is something that you're going to read like this is how you're going to address the main memory, right? So main memory itself is not doing any translation, right? So it's already dealing with physical addresses. So and then you retrieve the data word, maybe in some register. So that's where it's going to be stored. So why do we need this? Why do we need virtual memory? Well, one thing is that it allows to use main memory more efficiently. So effectively, sometimes we want to have, like maybe my laptop has 8 gigabytes of RAM, right? Well, actually it has 16 gigabytes, but doesn't matter, right? Maybe it has 16 gigabyte of RAM, but I want to have like maybe 32 or 64 gigabytes of memory. So, maybe on my disk, on my secondary storage, I can have additional space for that, right? So, so in other words, I want to be able to virtually support more memory than I really have. So, and the other way to look at this problem, that's one way to look at this problem as kind of putting something on the secondary storage. And the other way to look at this problem, and like when you look at a different angle, effectively you're accessing memory that is stored on your secondary storage using your physical memory as a cache, right? So that's another way to look at this problem. So your DRAM becomes a cache, right, for your disk, so to say. So that's the first thing that why you need virtual memory, virtual memory, right? So the second thing is simplify memory management. Recall that each process has to get this its own address space, and it's typically we want to get its own uniform linear address space. You're working on a malloc project. Whenever you want to extend the heap, it's just extended at the very end, irrespective of what other processes you have in your system. So you have this uniform linear address space in this particular process that you have full control of, right? So no one can allocate, because imagine what kind of mess we would have. Let's say in the heap, you have something, you need to extend the heap, but you cannot extend it at the very end because somebody already took that piece of memory. So you have to allocate somewhere else. So your memory allocate all of a sudden becomes even more complicated than it is right now, right? I'm not saying it's impossible to do that, but it's still going to be would be more complicated. So it's much easier to just extend your current address space. So still, I guess this is something that can be important, but maybe not super important. I guess one of the critical thing is the fact that we can isolate address space. So I think this is one of the most important thing that we have is virtual memory. So one process cannot interfere with another process memory. So your malloc program crashes, for example, right? That doesn't mean that other processes are crashing in the system. So it doesn't mean that your operating system will crash. So imagine how, like, what life would be if every time you have a bug in a program, you would have to reboot your computer. So that would be really bad, right? It would be hard to debug, and that's exactly what happens when you develop in kernel mode. You have to, one small bug can lead to fatal error, and you have to reboot the machine. And I mean, then you can debug it with virtual machines, but virtual machines also have to run on top of the hypervisor. At some point, you deal with this problem, right? Yeah, so, and it's possible to debug it, but much harder. And the user program cannot access privileged kernel information and code. That's very important, because otherwise malloc would just corrupt this, address space, and you wouldn't be able to recover from that. So the first thing is that using virtual memory as a tool for caching. So that's the first case. So conceptually, you treat virtual memory as an array of n contiguous bytes stored on disk. Any or secondary storage, doesn't matter whether it's hard disk or SSD. So by the way, what is byte? Well, yes. So in modern computers, 1 byte is 8 bits. But what is a byte fundamentally? Any idea? Yeah, because we are talking about bytes and megabytes, kilobytes. So what is a byte?
Standard unit storage.
Yeah, so I think the way that I guess the traditional, I think, definition would be that's the minimum addressable unit of memory, right? So you cannot address individual bits, but you can still address individual bytes. Even, let's say, your CPU word or memory word can be different, can be larger, still you can access individual bytes. So that's probably the right definition, right, for that. So yeah, so therefore conceptually you view it as an array of n contiguous bytes. So this is why I asked this question, right? So the byte is a minimal addressable unit, right? So, but but the content, so effectively you're gonna cache this whatever you store on disk in physical memory. As I said, just different angle to look at this problem. You can look at the problem that I'm using my secondary storage if I run out of memory in my physical RAM, right? But the other way to look at this, you use your secondary storage and just your physical RAM as some sort of cache to make things faster. So effectively addressing your secondary storage memory, but using RAM as to make it faster. So that's another way to look at it. So, and the contents of an array of the array on disks, right? So this is going to be basically cached in physical memory. So now, when we deal with physical memory and with virtual memory, as I said, we will have bytes as minimal units. Still, even though the minimal unit is a byte, the way that we're going to translate virtual memory to physical memory, we're going to translate entire pages, not individual bytes, right? So we're going to translate pages. So effectively, whenever we want to bring something from disk, we want to bring the entire page. So that block, the entire block is called the page, right? We want to bring this block from disk. It's going to be read to memory, right? So now page size is typically p, like p is like equals to 2 to the power of something, right? So by the way, why is it a power of 2 number for the page? Any ideas? So why can, like, for example, in x86, you have 4 kilobyte pages or 4096, that's 2 to the power of 12. Why can't we just use like maybe 3 kilobyte pages? Or, you know, maybe like 5 kilobyte pages? I mean, maybe 7 kilobyte pages. Yeah, think about this for a moment. I'll get back to this question, right? So why we need to have power of 2 number? Yeah, so but one way or the other, right? So we can translate a virtual memory to physical memory. So and when we use paging, you know, these pages in physical memory can come in completely different order, right? So they can come in different order than in virtual memory. So now the bytes within the page, they are going to have direct correspondence. So let's say within one page, byte offset 2 in the virtual page is going to correspond to the physical page byte offset 2. So byte offset is going to be directly transferred to the when we do translation. But the page translation doesn't have to happen like any straightforward way, right? So it can be any order of pages in physical memory. Doesn't have to be contiguous range. That can be completely different range of addresses. So why do we have this kind of organization? So recall that DRAM is kind of around 10x slower than SRAM, right? So this main memory that we have is a DRAM, right? So it's not the fastest memory out there, right? So certainly some memory that you can build can be faster. Like even your CPU cache is faster, right, than this, right? And you know, that's one example. But you know, the difference, I guess, between CPU cache and memory is still not as big as, let's say, with the difference that you can have with the secondary storage. I guess nowadays things are kind of changing because of SSDs, but still, even though we have fast SSDs, we also have fast DRAM, right? So, and that gap kind of continues moving, right? So let's not stay in the same place, right? So there is still, maybe the gap is not as big, but it's still pretty big. Maybe not 10,000, like maybe compared to hard disks, but still pretty big. So what does that mean? Well, that means that we have to deal with relatively large block sizes. So at least, as I said, 4 kilobyte block for x86. You know, sometimes for x86 32-bit processor, we have 4 megabytes pages. For 64-bit processor, we have 2 megabyte pages or 1 gigabyte pages even. So there is even a way to like sometimes create larger pages. But you know, the common, I guess the smallest page that you have, let's not go into too much detail about this x86 architecture, right? So, but you still have like the smallest page, the common one is 4 kilobyte. Yeah, so also, why do we have that organization, some sort of mix of software and hardware, right? Because like in case of cache, like in CPU cache, this is all done by hardware. Why do we need this any intervention of the OS here, right? So let's look at other you know, things, right? Maybe like we look at latencies, right? Oh, sorry, like latencies, and maybe how long it's going to take to bring this page. But you know, I guess there's other issues, right? So one issue is that any virtual, you know, any physical page, sorry, any virtual page can be placed in any physical page, right? So there is a lot of the mapping function is relatively complicated. So for caching, you may come up with some sort of hardware may come up with some simple mapping function, right? So they can keep track, like how many times you access that piece of memory, whether you need to keep it or whatever. All right, so it's not easy here because the mapping function is non-trivial. Also, not only that, but whenever you choose to evict some page from physical memory, those page replacements algorithms are also non-trivial. They're going to be complex and fairly expensive. So you may need some help from hardware, but probably still want to have flexibility to handle that in software. So also we have write back rather than write through. For example, for cache, we can have write through cache, but not for paging organization. So it's just a different way to look at this. But the most important thing that we have to understand that there is no easy way to implement everything in hardware here. So we have to have some OS intervention. So how do we enable that, right? So how do we enable that implementation? How do we enable mapping from our virtual to physical addresses? So we have a so-called page table. So in the page table is an array of page table entries that map virtual pages to physical pages. So effectively, again, so like let's not confuse virtual memory. Virtual memory, we said that conceptual is just an array of bytes, right? Then we talked about mapping. We said that we map one page to another from virtual page to a physical page. And now the page table itself that is going to basically enable this mapping is an array of page table entries. And the page table entry can be like 8-byte entry, right? If you're using 64-bit processor, and it's going to say, okay, this virtual address, this virtual page corresponds to that physical page. On this virtual page corresponds to a different physical page. So it's basically an array which implements the mapping, right? So for each virtual page, you have the corresponding entry which has a physical page address. It's like a level of indirection, right? Like you have an array of pointers effectively, right? The same thing here. So now it's not always, though maybe the difference is between array of pointers. Pointers typically we are dealing with bytes again. Here, when we do the mapping, we only need to deal with pages, right? So that's one thing to keep in mind, right? So we only need to translate virtual page to physical page. So that means it's we don't need to translate individual bytes, right? Okay. So some of these pages will point to physical memory. And they don't have to appear in the same order. They can be in completely random order, just the way I have shown one example can be totally different, right? So now on the disk itself, we may also keep some pages. So perhaps not everything can fit in the physical memory, and some pages are stored on disk. And maybe yet another pages like we see now, those are invalid pages. They don't really point to anything. They're not neither on disk nor in physical memory. So they just maybe some gap in a virtual address space. So similar to cache, we have the same idea of page hit and sort of page miss, right, or page fault. So we have a page hit when we reference a virtual memory word that is in physical memory. So it's already in physical memory. So we just read it directly from, we just go to physical memory and read it, right? So now another point, whether like how the CPU is gonna, whether CPU is gonna use cache or not, that's a totally different story, right? but at the very least, you know, we have this translation, we have physical, we have this page in physical memory. We don't need to do anything else, right? We are done. So this is DRAM cache hit. So another case is when we have DRAM cache miss or page fault, right? So in a page fault, we reference a virtual memory word that is not in physical memory. So that is, you know, perhaps it's somewhere stored on your disk, and you need to, you know, you need to read this page. But how do you gonna access this page? You need to evict some other page from physical memory first, and then you can place it in the physical memory. So let's take a look. So page miss causes a page fault. So this is going to be an OS event. This is going to be a trap. Remember, we talked about traps and interrupts. So this is the case where you get this trap. You were executing an instruction, and this instruction we're actually accessing some virtual address, and this virtual address is not in physical memory. So at that point, CPU will generate a trap, right? So so now you're going to go to the page fault handler, and you're going to evict some page from physical memory, and then bring this page from secondary storage. So the page for the handler selects a victim page, so-called victim page, to be evicted, right? So this is our virtual page 4 in our case, right? Again, the way that the OS is going to decide it is based on page replacement policies, and it's like a different kind of discussion that we're going to have later. But just assume for a moment that somehow we have chosen the best candidate for the eviction, and we evicted some page. So this page is going to be, of course, written to the secondary storage. And now we have to bring the other page from the secondary storage and put it there, right? So we have virtual page 3 instead of virtual page 4. And it's in physical memory. So now recall that after you're done with the trap handler, unless it's a fatal trap, right? You will have you can have an ability to restart from the same instruction. So there are two ways. Sometimes you want to exit from a trap handler after that instructions, and sometimes you want to restart the instruction. So in our case, we want to just restart the same instruction. So the same instruction will be repeated. So now it will say, okay, I have that page in physical memory. So now it's a page hit. So and therefore everything is fine, right? So then therefore we don't need to do anything else at this point. So this is how we can support fundamentally have a larger virtual memory than physical memory, right? So because we can keep it on secondary storage. So we can also have a case when we have some invalid page, maybe you want to do allocate a new page. Perhaps you had the heap in malloc, you decided to extend it, and you know, maybe the OS wants to extend it, right? So, but how is it going to happen, right? So, well, you can just allocate a new page in virtual memory. It doesn't mean that you have to immediately allocate it in physical memory, but at least you have to create a corresponding mapping and say, okay, this page is valid, this page points to some valid virtual memory. So that's the idea. So previously it was now no longer now, right? So let's look at the second. So any questions so far? So I think this use case is kind of common, right? So this is probably what you first think of virtual memory when you hear that, right? So that virtual memory can be much larger than your physical memory, right? Yeah, but that's just one case, right? So it's not the only reason why we need virtual memory. So the second case is that we use virtual memory as a tool for memory management. Right, so the key idea is that each process has its own virtual address space. So why is it useful? Well, the reason why it's useful is because we can view memory as a simple linear array. So that means is that, let's say I have virtual address space for process one. I have, stack, heap. It can just, it just can go and extend completely, like without taking into account of any other processes, right? It doesn't need to know about process two, process three. In fact, it doesn't really need to know about their existence at all. So also two different processes will, point to different physical addresses, right? So they will have different mappings. And sometimes, maybe there's shared mapping. Let's say if you have some read-only section for the library code, for like libc library, something that can be shared across two different processes, you can also do that. So this is where two different virtual addresses will point to the same physical address. So that is also possible. By the way, it's also possible within one process, within one page table, multiple virtual addresses can correspond to the same physical address and across processes. So if you want to do that, you can, if it's, doesn't violate isolation guarantees, then it's fine. So in this case, it's read only. This is why we will not be able to override this code anyway, right? So therefore, it's fine. So you can effectively scatter these pages in a physical address space. You can put it in any order, but you need to choose mappings also sometimes more carefully to improve locality. Because sometimes, even though it doesn't matter how you organize that stuff, it can go in a completely random mode. You still want to make sure that if possible, allocate a contiguous range of addresses that you can improve some performance, improve locality, and so on. So how is it simplifying like linking and loading? Well, for linking, things are easier now because we have the same virtual address space, right? That means whenever I want to generate code, data, I don't need to worry about other processes. I just need to think about this particular process. So code, data, heap can always start at the same address. So that is generally true, except when you use ASLR, address space layout randomization. So remember with ASLR, I think I briefly mentioned in the beginning, maybe several lectures ago, right? That with ASLR, we can have an ability to randomize addresses for security reasons. But still, even with ASLR, we are worrying about just one process. We don't need to worry about gazillion of other processes that we have, right? So we just even the randomization that we do, it's within a single process. So this is in terms of linking. So in terms of loading, how can it help us? Well, in terms of loading, recall that whenever you load a program, you will have, by the way, is battery, can you still hear me? Okay, I think the battery is, okay. Yeah, so recall that whenever you want to execute a program, let's say you execute something in a shell, and in the shell, you start some command, and initially a shell is going to do fork. So fork will create a child process, which will be the same kind of copy of the parent process. initially, right? And then you call exec to substitute that child process with whatever executable image you want for the corresponding command. So now at that point, you can just say, okay, I have these text and data sections. They contain pages, basically, for that process, right? So you can just bring them later, right? So I'm just creating a mapping in virtual address space, but I don't necessarily need to bring them immediately to the physical memory. That can be done later, because now this file itself can be like executable file itself becomes like part of this mechanism of virtual memory, right? And likewise, there are really kind of read-only regions, especially if there's read-only code. There is no need to write this stuff because this stuff doesn't change, right? So it's going to stay the same. So what you can do, you can copy text and data on demand, just one page at a time. You execute this instruction. You don't have this physical page in the physical memory. You get a page fault. In the page fault handler, you read this file, you read that corresponding location, bring this page and put it in a physical memory. So that way, even if your process is really big, like several gigabytes of memory, you're not gonna spend time reading that file right away. And sometimes there is some code you're never gonna read. Maybe there's some function that is only executed under some special circumstances, right? So it's not gonna be executed, and you're not gonna waste time even reading that from the disk. Okay. So yeah, so that simplifies both linking and loading, right? But there is one even more important thing that you can, I guess you can still argue you can get away with this. You can have position independent code. Maybe you can have a more complicated memory allocator, which decides what kind of memory regions to use or not use. Maybe it complicates a lot of things, but you can still get away without it. But there is another reason why we need virtual memory. This is for isolation. So you want to really make sure that this particular process can only access these pages and nothing else, right? So only this specific range of pages. And it also means we don't want to allow this process to access kernel memory. So we have some kernel level pages, we don't want to allow those. So recall that previously I mentioned that pages can be both in physical memory and the disk, right? So how do we determine this? Well, there can be a bit, a special bit called presence bit, right? So it will indicate whether the page is currently present in the physical RAM. So in addition to this presence bit, we can have a whole bunch of other bits, like so-called permission bits. As one example of the permission bit is a supervisor bit. So what that means is that for each page, you're gonna set, okay, can I access that only from kernel space, or can I access it from both kernel and, so can I access only in kernel space, or versus can I access in both kernel and user space? So that's what the supervisor bit is. So like for user code, you can access it in both kernel and user space. There is no problem about this, right? But for kernel code, you want to make sure kernel code and data, you want to only make sure that only kernel can access that stuff, right? Not any user process. More importantly, let me actually draw that. Yes, so So typically the way that it works, it's not just you have a separate virtual address space and separate page table for each process. But also one, let's consider a process, just one process, right? It has its own virtual address space. We also want to split it in two kind of pieces. One is going to be user space and the other is kernel space. I mean, it doesn't have to be done like this. Can be like you can even arrange pages differently. There is no requirement to be on top or on the bottom, right? Because as I said, one permission bit determines whether this corresponding page can be used in kernel or user space, right? So it's much more flexible in this. But one thing that you can do is, let's say you have 2 to the power 64 address space. You can say, okay, this is 2 to the power 63 for user and 2 to the power 63 for kernel. And then you're going to have some mappings here in user space. That's going to be your physical RAM, right? Maybe something else here. And then that's going to say user one, right? So accessible from user space. And then maybe there is another thing, right? So there is a kernel code or something like kernel data points to some other region of memory. That's going to say user 0. So for each page, you're going to have this bit. So why is it useful? Well, when you have a system call, for example, right? Well, remember we talked about system calls. System call is a special kind of trap when you want to execute some kernel function, right? So you're not allowed to execute an arbitrary function. You're only allowed to execute some specific kernel function, which is known as system call. So you're gonna have some system call, right? But you don't want to switch page tables at that point, right? So in fact, that's how it's done in x86, that all processes will have the same kernel address space, right? So they will effectively have exactly the same mappings for kernel space. So user space for everyone will be different, but kernel space will stay the same. Well, except that this, meltdown bug I mentioned last lecture, right? So this kind of makes things a little harder, but let's just put that aside because it's a CPU bug and there is a workaround for that, right? Let's assume it's a bug-free CPU. Yeah, so you have another kernel address space, which can have this exactly the same mapping, right? So exactly the same mapping in a different process. Okay, let me go back to the slides. So this is why we may need supervisor bit, right? So we can say for the page whether it's only accessible from that range or not, right? So like whether it's accessible only from user space or whether it's accessible from if it's accessible from kernel space only or whether it's accessible from both kernel and user. So don't get confused. It says user and kernel, but user implies it's also accessible from kernel, right? So kernel means only kernel only, user means both kernel and user. Because kernel can always access any memory. Okay. So for each page, we have the address and associated bits, right? So whenever we create a page table, we have a page frame number that's going to say this just the page frame, right? So that doesn't have to have a byte address. It can be just page number. So how is page number different from byte address? Well, if let's say I have byte address of let's say 0, 4096, 800192, right? And so on, right? That's the byte address. So in terms of page number, that's going to be 0, 1, 2, right? Assuming that the page is 4 kilobyte. So it's divided by the page size, right? So in addition to this page number, you will have this bits, right? So you will have the supervisor bit. You will also say whether this page is read only or writable or whatever, whether it can be executed. Also, you have this present bit and many other bits. So why do we have a page table per process and not a single page table for the entire system? Okay, go ahead.
You define the pages related to the program.
Well, but that's one thing, right? But what is the thing that we have just discussed, right? So aside from the reason, okay, go ahead. Yeah, isolation, right? So because we want to isolate, right, things. So why is the page table has to be inside the kernel part of the address space? So I didn't mention that, but you know, that's kind of natural that we have to keep that in probably in kernel space. Why? So why do we need to put the page table in this range, somewhere in this kernel, right, range? So the page, okay, go ahead.
So you need like increased privileges to see what processes are actually on the computer, or like see what page tables are there.
Well, but why can't, like, let's say this is process one, right? Process one. Why can't I just keep the process one page table inside user space? Somewhere just maybe allocate from malloc or something like this and be done with this.
Like in isolation.
Yeah, so but what problem is isolation, right? Can you elaborate on this?
You say that again?
What problems with isolation will arise? Can you elaborate on that?
Accessing other processes.
Yeah, so like an example, right? An example would be when you deliberately specify some memory address that you don't have right to access, right?
Buffer overflow.
Well, buffer overflow is a different thing, right? So for example, you will have a page table, and in the mapping for that page table, you will say, okay, I'm gonna access page maybe 1M, right? So, and that 1M page belongs to a different process, right? So but you know, because I can manipulate page table directly from user space, this program can trick the system and basically access this page, right? So now this is why we don't want to allow that in user space. We want the OS to deal with the page table. So only the OS can modify the page table, and therefore, the OS has the ability to verify whether this page really belongs to this program or not, right? So this is why we want to keep that inside the kernel part of the address space. So that's important, right? So because we don't want to make the page table itself accessible to user. So if the page table entries for the OS are contained in the process page table, how is the process prevented from accessing OS memory? So because for the OS, I mean kernel, right? So there is page table entry for this kernel, right? For the kernel piece. So how is process prevented from accessing OS memory? Yes. So because you have current privilege level, it says, okay, you're on user mode. There is a supervisor bit set. Okay, it says, okay, there is some problem. I will generate a trap, right, and let the kernel to figure out what's going on there, right? And you know, at that point, kernel say, oh, somebody's trying to access my memory. It's not allowed to, right? So let me terminate this process. Okay. So, okay. So when we by the way, I previously talked. Yeah, that's going to be the next slide. Let me mention that later. So let's first define how virtual address translation happens, right? So we have the virtual address space. The way that we can treat virtual address space is some sort of a set of addresses from 0 to n minus 1, right? The physical address space is the same deal, right? From 0 to m minus 1. Again, you don't need to consider bytes. We really consider pages. So that's basically just frame numbers. So the address translation is going to be some mapping function from virtual to physical, or like here shows an empty set. You know, for some entries you saw that we specify null pointer. That means we don't really have any mapping at all, right? So that means there is no mapping to any physical memory. So there is for virtual address A. So map A is going to correspond to A prime if data at virtual address A is at physical location at A prime, right, in P. So, and also we can define this function as empty set, right, if the data at virtual address is not in physical memory, right? So that means it's invalid or stored somewhere on disk. So there are two cases. So let me go back to this picture. There are two cases here. There is a case when you see this gray, right? So there is gray color when it's in disk. And then there is also a case when it's white and has null pointer, right? So that means it's invalid. So only this valid, like only this, but for other case, we have this mapping, right? From virtual to physical. So that's how we would define this mapping function fundamentally. So let's also look at some address translation symbols, and we'll wrap up here. So the number of addresses in virtual address spaces can be n to equals to 10 to the power small n, right? So maybe you have 2 to the power 48 for 48-bit virtual address space. So that's how we can define that. Now, number of address, physical address space, 2 to the power of m, all right? So that can be maybe my laptop has 16 gigabytes, so that's going to be 2 to the power of 34, right? So that's going to be corresponding how many bytes. Again, addresses we have to be more clear here whether it's bytes or frames, right? Here I didn't specify. Typically, I would specify that. So now the page size is also 2 to the power of something. So why do we need a page? I think I previously asked that question, right? Why do we need to have a page 2 to the power of something? Any ideas in terms of the translation? Okay, let me kind of draw like a picture here. So we have, let's say we have a 32-bit virtual address, 30-bit virtual address. So what I can do, I mean, ideally what I would want to have, I want to have like page number, page frame number, and then byte offset, right? And that's the entire thing is like byte virtual or byte address, right? So byte address. So that's byte or memory byte address, right? So whatever you think, like maybe your pointer, right? So I want to take your pointer, like a virtual address that you specify in your program, and easily get the page frame number, right, as well as the byte address. So if I use power of two numbers, for page sizes, that's going to be easier. So you can just find it now like 2 to the power of 12, right? So if it's 2 to the power of 32 divided by 2 to the power of 12, it's the page size, that's going to be 2 to the power of 20. So it's going to be 20 bits, the page frame number, and 12 bits, the byte offset. Right, assuming that the page size is 2 to the power of 12. So when you use 2 to the power of something, as opposed to, let's say, 3 kilobyte or 5 kilobyte, you can easily have that component here. Right, so because we are dealing with binary numbers, right? So therefore, 2 to the power of something, right, is gonna help us to directly split that in here, right? So because otherwise we'd have to do expensive division operation, right? Here we don't need to do any division, we just split takes part of this bits for the byte offset, part of this other bits for the page frame number. So this is why we use power two numbers for page sizes. Now for memory size, it's I guess for virtual address space, it's also 2 to the power 48 or like on modern computers, right? Sometimes they also support larger than this. But I guess for physical memory, not necessarily we can have 2 to the power, I mean, sometimes you can have 12 gigabytes as opposed to 16 gigabytes. But still the physical address line will probably have 2 to the power something, right? So it still would you still have to have support. I think it supports like, and my computer probably says 39 bits physical address or something like this, right? So it still has 39 probably lines, right? 39 bits. Okay. So and then the components of physical address and virtual address is their offset, physical page number or virtual page number, and physical page offset or virtual page offset. Right, so this is like two components, right? So that we will deal with. So also TLB index and TLB tag, but that we will talk later, right? So and let's stop here. Let's continue our next lecture.